usual is that we actually have two layers of hidden variables. We don't know what the states of the model are. We don't know what the states of these mixing components are. We can solve this as usually in problems that involve hidden variables. We can write down what the EM algorithm is, or the expectation maximization algorithm, which is sort of the standard tool for learning the parameters of models with hidden variables. And in this case, it boils down, the expectation step. We basically have to run a Kalman smoothing filter to collect some expectations and covariances, and from those we derive some statistics, and then in the end step, all the parameters of the model get updated based on those statistics. I'm not going to go over this in detail because it's sort of technical and
So do you only learn the parameters based on a fixed structure, or do you learn the structure first on your training data?
Right now, we've done several things. For the purpose of this talk, we're just learning, we're not learning any structure. We have a mixture of, say, five dynamic systems, and we're just learning the parameters. But there are, in fact, we've done a lot of other things like, layers of dynamic textures and things like that. So there's a lot of things you can do. But for the purpose of the talk, I'm just, talking about like the simplest possible, model. Okay, so that's the model. What can we do with this? Okay, the first thing we can do this is video segmentation. I already sort of hinted at how this is done. So we have video of, say, this pedestrian walkway. We extract these spatial temporal cubes. We learn the mixture. Say in this case, if I have two flows, people going away from the camera and towards the camera, I learn a mixture of two dynamic textures or two linear dynamic systems, so that those are represented here by this, Gaussian-like type of blobs, and then I can assign. So at each point, I can find what is the of these components of the model, what is the one that has highest posterior probability given the video observations at that point. Okay, so from that I can segment the video. So if I have new video, once I learn the model, I can extract these cubes. I can compute the posterior probability of the observations under each of these components. And if this component has higher probability, I label 1. If this component has lower probability, I label 0. I can do that at all locations of my video, and from that I can derive a segmentation mask that tells me, things that are in the same class have the same color. So it's like a traditional segmentation mask. Okay, so it turns out that if you do this, you actually get sort of a segmentation, motion segmentation algorithm that actually works fairly robustly. So this is, video that sort of we collected just by putting a camera, outside of, one of the windows in our building. So it's totally not. So it's it's whatever the motion is. If you go to my website, you can have, you can literally watch, it's like hours of video of this, okay? It's very robust. That's the fundamental, property. As you can see, these are really sort of complex scenes. People are going, sometimes they group, sometimes they cross each other. They're doing whatever they want to do. And the model, if you use this model, it just runs. We don't have to initialize it or whatever.
Yeah. How do you decide when to do individual trajectory-based analysis versus when to do this level?
Well, that really depends on what you want to do, and I'll get to some of that later on.
Because I could do an individual trajectory level analysis here on this video, for example.
Sure.
It's actually very similar to the video USC Nebati has been working on for tracking and.
Well, but the problem there is, what's the scalability, and then once you do that, you have trajectory.
So it's just scalability. When do you do individual trajectory, and when do you transition to this kind of an analysis, where you say that you cannot do individual trajectory-based analysis anymore?
Well, I mean, that's, I don't know. I mean, I haven't been looking so much at that transition. I've been looking more at like, how do we, solve the problem on this side.
What about if you have 20 people?
I mean, I do think that if, I mean, we've been, let me show you a few more things. I mean, we've been working on this on like videos where it's really hard to sort of, things are small and there's not a lot of resolution and so forth. So, I know that, and on the other hand, we can do things with these models that, you would use as a justification for doing individual trajectory
You give
analysis.
the physics analogy, for example.
Right.
So in physics, you can transition from an in-body problem to a fluid motion problem.
Right.
Or a gas, so the example that you gave. So, here also, if we have that analogy, then at some point you have individual particles that are moving around. You can analyze the motion of those particles.
Sure.
And at some point you say that I cannot analyze those particles.
Well, I mean,
individually.
I don't think it's that much what you, I mean, it's more like what do you want to do? If what you want to do is a measure global properties, I would say you should never do individual analysis. That's my position. If what you want to do is measuring properties of the crowd, okay, I would say don't use, individual object analysis at all, because that's just more complicated.
Yeah, but I could have the question here that what would be, so identifying examples of people walking together.
Sure.
Then it would be difficult to do that at the crowd level without individual trajectories.
I would dispute that.
Or maybe a person walking to a car. So let's say there was a parking lot here and you had a car and a person walked to the car.
A single person, well, it could be, if that's what you want to do, but then you're not talking about a crowd property. You're talking like, I want to identify a person walking to
Yeah,
a
but it
car.
could happen with everything else going on here.
And that's fine. But then, I mean, I'll talk about a little bit doing anomaly detection in these scenes, and then you're trying to find anomalies, and that by definition is like one person or one, and that's fine. I mean, then you're talking about sort of individual processing. But say if you're talking about like how many people are walking around, that's not an individual task.
Right.
And so I mean that's really that's really the what I'm talking about here. Not so much. I mean if you wanna identify Mr. X, well that's not a crowd property. You have to recognize him and you have to track him and so
What
forth.
about to answer this question in a simple manner, when the density of the people or particles in a given volume becomes high, then you want to have crowd. Then that's what the interest is. So you cannot do single person kind of
Right.
thing.
So but to get the density, you need individual counts. That's
No, we
how
don't.
you can
No,
compute
we
the
don't.
density.
But he's
No, you don't.
watching over time. I mean, things are.
No, you don't. I'll show you don't. But see, but the problem with that is that I would say that even if you don't have a lot of density, there's a lot of things you have to do without tracking individual people. And and you can do it in this way too, and it's easier. I'll show you. I mean, I'll go ahead.
In space and time, if there is
Right.
in this volume, if there is a high density,
Right.
then there is a switch. You turn it
I'll
on to otherwise turn
I'll
off.
show you some examples of that. So let me go on and then I'll show you. Go ahead.
Oh, and the novelty of this seems to be that you're using textures to model the flow of the crowd, is that correct?
Well, that you're not using, see the idea that we're looking at here is that you're not using sort of individualized processing.
So is it, what are the advantages of this over, say, optical flow?
Well, because optical flow doesn't really, allow you to do this, it breaks. It doesn't. You can't really do this sort of, it's much less robust
Okay.
because it's just a local model. And we've tried, we've tried to do this sort of segmentation with optical flow, and you can do something, but it doesn't. It's less robust.
Okay.
That's the.
How it's related with the Ahuja's work?
They've done some work on, dynamic textures too and stuff like that. Yeah, it is the same type of, they have some alternative dynamic texture models that could be used for you. So let me just, just show you some examples. Okay, so here are some some things. So these are just some simple examples of the things that we built with this model. Okay. So you already saw the segmentation. So here's another example. So this is like video clustering. So this is the same model, the exact same model, but now applied, instead of being applied to pixels, applied to the entire video frame. Okay, it's just that now my components. So I have a database of videos, and I fit fit this model to the database of videos. Okay, and that gives me a way to cluster the video. And if you try to do that, so what this does naturally is that, so this is just the result of clustering the video with a mixture of 6 components. And what you see is that naturally it clusters the video by the similarity of appearance and dynamics. And it tends to group things by how congested the traffic is. Okay, so this is real video from a webcam that's available on the web from the Washington State Department of Traffic. Another example shown here is just classifying traffic congestion. Okay, we learned these models, and then from the parameters of these models, we build a classifier that just says determines what is the level of congestion in this city. Okay, again, so this is videoed from the. So the label is shown here on the upper left, and so as you can see here, I mean there's lots of variation. Sometimes it's raining and there's drops. So you see here it's really hard to even see the objects in the back there because it's it's kind of raining and foggy, and there's drops of water in the camera and so forth. And the point is that this is a really what am I trying to do this here? I'm trying to say whether it's congested or not, and it is overkill to sort of use try to track all the cars and so forth and reason in terms of the cars in order to do that. Okay, this is a slightly different application. This is more along the particles of crowds type of scenario, where we're doing background subtraction, which is sort of a classical problem in vision, which is easy to do when the background is static, but it's not as easy to do when the background is moving. And so this is using the same models to learn a background type of model. And so the idea is every time you see something that doesn't have a lot of probability under the model, you declare it as something that's not background, it's foreground. And the difficulty here is sort of dealing with this sort of waves that are left when these objects move. And so by using this type of models as background models, we obtain a lot more robustness to that sort of thing. So this is the difference. You're asking what is the difference between doing optical flow and these types of models? That's the difference. You would never be able to do this with sort of an optical flow model unless you build a lot of stuff on top of it. Just because locally the motion is very, there's a lot of motion that's different than over time and over space, unless you have the ability to model, you have a spatial temporal model of appearance and dynamics, it's really hard to do it.